Physics, Part 71. Calculate the applied stress, the strain, the extension of the wire. Number 2, elastic band of an area across the section 2.0 millimeter square has an extended length of 8.0 centimeter. When stretched by a force of 0.4 Newton, its length becomes 8.3 centimeter. Calculate the Young modulus of the elastic. The behavior of different materials under tensile stress. The force extension graphs of all metals in the form of the wires have general shape shown in the figure. Straight line portions through the origin, the Young modulus is measured in this linear region, and then a region in which the extension increases more rapidly than the force, eventually well into the region of plastic deformation. Application of the larger forces will cause the cross section of the wire to form a narrow neck so that the extension continues to increase without addition of further force. The wire eventually breaks. From the force at which the curve is a maximum point x, a quantity known as an ultimate tensile stress can be calculated. This is the maximum force divided by the original cross-sectional area and the wire, not the area of the narrow neck, which would be almost impossible to specify. The ultimate tensile stress gives an idea of the maximum stress that the wire would support. Note that this is not the same as the stress when the wire finally breaks. Note also that for the terminology, breaking point is not satisfactory, and it is not clear to what the point refers. Is it a position on the wire, length at which the wire breaks, the force required to break the wire, the breaking stress or the breaking strain? Well, the figure is characteristics of the material which can be drawn into wires or ductile materials. Ductility is a characteristic of many metals. Another fiber is a typical example. The fiber extends elastically with a linear relation between force and extension over an appreciable range. Very soon after the limit of proportionality, the fiber snaps. This is called the brittle fracture, and many amorphous substances like glass are classified. Brittle materials, their characteristics is that deformation obeys Hooke's law over practically the whole range of extensions. There is very little, if any, plastic deformation, shatters into many pieces. The glass is incapable of plastic deformation, and if breaks, a metal beaker, on the other hand, is deformed plastically by the impact, ending up with a permanent deformation in the form of a dent, but not breaking. Force extension graph for brittle material. Typical polymetric material such as rubber has another entirely different force extension graph. This is sketched in figure for a rubber coat. Only a very small part of this curve. There the origin is sufficiently linear to use it calculate the Young modulus. An important point to note is that the cord can be stretched to many times its original length before it breaks. The curve also shows a very extensive region in which the cord will return to its original length. When the stretching force is removed, however, this may not be the case of simple elastic extension, because although the cord is not permanently deformed, it may not return to its original length along the same path. This is called elastic hysteresis.